Hey everyone, welcome back. Today we're going to talk about vector fields, what those look like, talk a little bit about sketching them, and then also maybe trying to talk about some strategies on how to, if you're given a function, match it to a vector field that you've also been given. So, well, I mean, first and foremost, what is a vector field? It is really actually kind of what it sounds like. It is a collection of vectors that we've placed on either the XY plane or in 3D space. And it's just, we take a point, we plug it into a function, and then that function tells us what vector goes there. And that's the vector field. And we can do this in the 2D case, which might look a little bit like this. F of xy equal to some vector that also has two functions as its components. So say f1, that is a 1, not like a prime or something like that, xy, and then f2 xy. Or we can also have the 3D case where we take a 3D point and plug it into a 3D. We get a 3D vector out of it. Just like so. Okay, so main idea here is that it takes in a point and it gives you a vector at that spot. Great. Okay, so let's look at some examples of what this looks like. Our first example is, well, I mean, the two examples that I'm going to draw are going to be in the 2D case because the 3D case is really quite tough to illustrate with this. But we're going to take fxy equal to the vector 2x, 2y minus 2. So if I wanted to sketch this, I'll go away. I'll draw my xy plane. I'll put some tick marks on it. And to be able to draw this, so we can employ a similar strategy to what you might use in, say, like college algebra or something like that when you don't know what a function looks like. And we'll set up this table and put our xy points or xy coordinates here for the point that we're looking at, and then what we get out of it is a vector. So if I wanted to say, look at the point 0, 0, 0, 1, 1, 1, -1, -1, stuff like that. You can try as many points as you want. I just take those points and plug them in, and it'll give me the vector that should be at that location. So let's start with 0, 0. If I plug 0, 0 into my function, what I'm going to get back is the vector 0, -2. If I plug 0, 1 in, I'm going to get the vector 0, 0. If I plug 1, 1 in, I'm going to get back the vector 2, 0. And if I plug in -1, -1, I'm going to get back -2, -4. And now at this point, what I can do is go in and plot these on here on my XY plane just to see what my vector field would look like. So at 0, 0, I'm going to place the vector 0, -2. Oh. 0, 0, vector 0, -2. So that's 0 in the horizontal direction, and then -2 is going to go downward 2 units, like so. Okay, 0, 0, the vector 0, 0 is going to go at the point 0, 1, which is right here. So I don't really draw a vector really in any direction there because that is the 0 vector. At the point 1, 1, I'm going to get the vector 2, 0. So it's going to be 2 units to the right and 0 units up and down. And then at the point -1, -1, I'm going to go 2 units to the left and down 4 units. So my vector is going to look something kind of like this. Now, as you can probably imagine, based off of the vectors that I've drawn already, as you put more and more points on here, the vectors are going to kind of start to run into each other when you draw them. And that's totally okay. When you're drawing it by hand, it's really not that big of a deal. And that's really actually quite to be expected. It doesn't really mean anything that they're bumping into each other. There's no mathematical significance behind that. It just means that our drawings are, cramped and things are bound to overlap and stuff like that. Not a big deal at all. But that's part of the reason why if you look at pictures that are in textbooks, like we're actually going to look at here in a few minutes, that they will have rescaled all of your little vectors so that way they're not bumping into each other. And like I said, we'll look at an example like that in a second. But before we move on to that, I do want to do one more example for you of kind of how to plot these things on a plane. Okay. So, all right, so for this one, we have f equal to sine of y, and then x. And here's our coordinate plane again, x and y. And let's make our table here. All right, so let's look at the points 0, 0. We can do 1, 0, 0. And then I'm actually going to use pi over 2 for my y coordinate because I'm looking at sine. And then 1, let's do pi over 2 again. All right, so if I plug in 0, 0 into this, I'm just going to get back the vector 0, 0. Not terribly exciting. If I plug in 1, 0, I'm going to get back the vector 0, 1. Because the 1 goes in the x, in for x there, and it's in the y component, so it's a little bit backwards. If I plug in 0 pi over 2, I'm going to get, well, the pi over 2 goes into sine y, so I'm just going to get 1, and then the 0 goes in for x, so I'm going to get 1, 0. And then on this next one, I'll get 1, 1. Okay, so for my tick marks, I guess I'm going to want something that's like 0, 1, and then there's a 1. And then I'm going to note that pi over 2 is it's roughly 1.5, maybe a little bit more than that. So I'm going to look at right here or so being my pi over 2. It doesn't have to be exact. Okay. So at the point 0, 0, I'm going to have the 0 vector. So I'm just going to have like a little dot right there. At the point 1, 0, I'm going to have the vector 0, 1, which points straight up 1 unit, like so. At the point 0, pi over 2, I'm going to have the vector 1, 0, which points directly 1 unit to the right and nothing up and down. And then at the point 1, pi over 2, which puts me right here at the end of that other vector, it's going to point 1 unit to the right and 1 unit up. So it's going to go like so. And so you can kind of see what this vector field is going to look like as you put more and more vectors here. And again, they'll kind of run into each other, but we're really not too terribly worried about that. And a lot of times you won't be asked to draw them too terribly much anyway, because again, the artistry on them is kind of a pain. But what is really popular is that a lot of times they'll give you pictures of them and then ask you to kind of match them to different functions. And this is just kind of an image of what they look like once they've been all filled in, all the different points or all the vectors at different points and stuff. And through this, you can actually kind of get an idea of the shape of the overall, just, how everything's moving and where everything is pointing and stuff like that. But the idea behind how to match these to any function that maybe you've been given, and I'm not going to work a specific example on this, but I want to kind of talk through it, is you can, so to match vector fields to their functions, I mean, you really just have to do what you do above, plot a few vectors, see if primarily you want to focus on the directions and relative lengths. Match any of your images. Because a lot of times, like I said, they'll rescale the vectors just a little tiny bit so that way they're not just bumping into each other. As you can see, none of them are overlapping here. So I mean, like maybe some of yours overlapped in your pictures. Imagine what would happen if they were all just a little bit shorter, so that wasn't happening. Just focus on the direction that they're pointing, and if they are just simply shorter or longer than their neighbor, as opposed to being exactly 2 units in length or something like that. So that's kind of the big idea behind to make those matches. So Now, if we want to look at the 3D case, here's what these graphs look like. And again, they're really quite tricky to draw by hand. So a lot of times the problems that you'll be looking at is that you've been handed a vector field function, and then you're asked to match it to its picture. So for the 3D case, here's what you want to look for. And actually, I mean, like, you can kind of use these strategies in general, actually in the 2D case as well. But the 3D case, you can't really do the whole starting with plotting a few vectors thing, because that's really tough. So anyway, in the 3D case, the first thing you want to check is, does the direction of the vectors depend, or do directions of vectors depend on their location? So for example, if you have that, say, f of x, y, z is equal to 2, 2, 2, then if we look at what this is saying then is that regardless of where it's located in the space, any x, y, z that we plug into here, we're always going to get back the vector 2, 2, 2, which means that at any single point, any single location, like say right here versus right here versus right here, we should be expecting to see that all the vectors are pointing in the exact same direction, and that they aren't really just like going in different ways. So if we look at A, all the vectors are pointing in different directions depending on their location. So that's really not going to be a great option for this particular vector field. But if we kind of look down at C though, see how they all point in the same direction regardless of where they're located at, like they're all pointed up and to the right, regardless of their location. So that's really probably going to be what goes with this example here. So you might go with C. So, and again, I do want to emphasize that a lot of times these get rescaled a little bit just so they don't run into each other, so the images are a little bit clear, but their relative lengths should all be kind of more or less the same. And that actually kind of brings me into my next point here, is you want to check to see if the length also depends on their location. So here's a little bit trickier example. Suppose that we have f, x, y, z equal to just the vector x, y, z, but then we divide by its length. So since the vector x, y, z is always being divided by its length, we know that this whole vector here has to have length 1. However, since we are actually plugging in x, y, and z, we can't expect their direction that it's pointing to change. It just will always have the same overall length. So we can look at A, B, and C, and we notice that of these three, or A, B, and D, excuse me, if we look at A, B, and D, they're all pointing in different directions. So that kind of matches that criteria there, that the direction does indeed depend on the location. But if we look at D, the lengths of these vectors are all the same, regardless of where they're located at. So that means that we're probably looking at D for this one. And then after that, you can kind of use some process of elimination and or note that, you know, all right, suppose that you've already made the identity for C and D, but suppose that, okay, D and B look really similar in kind of shape. They're both all pointing outwards away from the center. Well, maybe the function that goes with B looks really similar to D, but it might not have the scaling idea here. So, but anyway, that's kind of the idea behind how to identify these things. This is what vector fields look like, and vector fields play a really, really important role when you're working in a wide variety of applications in physics, like with electromagnetism and fluid dynamics and stuff like that. A lot of really, really cool applications, and the stuff that we're going to do in the videos coming up is actually going to further these ideas that we're learning here with this, and then also take them and apply them to some other concepts. So I'll see you guys next time.